Let yourself settle into this moment wherever you are. Take a slow breath, feeling your body relax into comfort. Tonight, we're going on a journey through time itself, but there's no need to rush, no need to strain. Just listen, let the words wash over you like gentle waves, and allow yourself to drift as we explore one of the most profound questions humanity has ever asked. How old is the universe? It's a question that seems simple on the surface, yet contains within it the entire story of existence itself. Every star you've ever seen, every planet, every atom in your body, every moment of history, all emerged from a single point in time that scientists can actually measure. And the answer, when you really stop to think about it, is almost impossible to comprehend. The universe is approximately 13.8 billion years old. 13,800,000,000 years. Try to picture that span of time. All of recorded human history, every civilization that has ever risen and fallen, every human who has ever lived and dreamed and wondered at the stars above them, all of it accounts for less than 1/1,000,000th of 1% of the universe's lifetime. We are newcomers to an incomprehensibly ancient cosmos. But how do we know this? How can scientists measure something so vast, so far beyond human experience? And why, despite all our sophisticated measurements, is there still debate, still mystery, still so much we don't understand? As you relax deeper into comfort, let's explore these questions together. We'll travel back to the very beginning of time, witness the birth of the first atoms, understand how scientists decoded the universe's age from whispers of ancient light, and discover why this seemingly settled question has recently erupted into one of the biggest controversies in modern physics. The question, how old is the universe? The age of the universe is not just a number. It's a story written in light that has traveled for billions of years to reach us, encoded in the motion of distant galaxies, hidden in the faint radiation that fills all of space. For most of human history, people believed the universe was eternal, stretching infinitely backward and forward in time. The night sky seemed unchanging, permanent, a fixed backdrop against which human dramas played out. This perception began to shift in the early 20th century, when astronomers started to realize that the universe was far stranger and more dynamic than anyone had imagined. The story of how we came to know the universe's age is really the story of how we discovered the universe itself, how we learned that the cosmos has a history, a beginning, and perhaps an ending. Today, the most precise measurements from multiple independent sources converge on a specific answer. The universe is 13.787 billion years old, give or take about 20 million years. This figure comes primarily from observations of the cosmic microwave background radiation, a faint glow that fills the entire universe, captured most precisely by the European Space Agency's Planck satellite between 2009 and 2013. Think about the precision of that measurement for a moment. Scientists can tell us the age of the entire universe to within 20 million years. That sounds like a huge margin of error until you realize it represents an uncertainty of less than 0.2%. Imagine trying to guess someone's age to within 0.2% accuracy. For a 50-year-old person, that would mean guessing their age to within 2 months. For the universe, we've achieved something similar across nearly 14 billion years of cosmic history. But here's where things get interesting, and where you might notice your mind becoming pleasantly fuzzy as you drift towards sleep. Different methods of measuring the universe's age don't quite agree with each other. The cosmic microwave background method gives us about 13.8 billion years. But when astronomers measure the current expansion rate of the universe by observing distant galaxies and supernovae, and then work backwards to calculate when everything must have started, they get a slightly different answer. The universe, according to these local measurements, appears to be expanding faster than it should be if it's really 13.8 billion years old. This discrepancy has grown from a minor curiosity into what scientists now call the Hubble tension, named after Edwin Hubble, the astronomer who first discovered that the universe was expanding. Some recent measurements suggest the local universe is expanding at a rate that would make it only about 12.8 billion years old. The difference might not sound like much, but in cosmology, a billion-year disagreement is enormous. It's like finding two perfectly accurate clocks that somehow show different times. This tension is exciting rather than troubling, though. When measurements don't agree, it usually means we're on the verge of discovering something new about how the universe works. Either our measurements have subtle flaws we haven't found yet, or more thrillingly, the universe is behaving in ways our current theories don't predict. Perhaps dark energy, the mysterious force driving the universe's expansion, hasn't been constant throughout cosmic history. Perhaps there are new particles or forces we haven't discovered yet. Perhaps the universe is even stranger than we imagined. Let yourself relax as we consider this. The universe is almost 14 billion years old. 14 billion years of stars being born and dying, of galaxies forming and colliding, of matter and energy dancing through the darkness of space. And we, here in this present moment, have the extraordinary privilege of being able to look back across all that time, to decode the universe's history from the light that surrounds us. The story of how scientists determined this age is equally remarkable. It required piecing together evidence from multiple sources. The motion of galaxies, the ages of the oldest stars, the chemistry of ancient stellar remnants, and perhaps most importantly, a faint microwave hiss that permeates all of space. This cosmic static is actually the afterglow of creation itself, the cooled remnant of the titanic energies unleashed at the universe's beginning. Every discovery built upon previous ones. First, astronomers had to realize that the fuzzy patches of light they saw through telescopes were actually distant galaxies, island universes containing billions of stars, separated from our own Milky Way by unimaginable gulfs of space. Then they had to measure how fast those galaxies were moving. Then they had to understand what that motion meant. Then they had to develop the physics to model the universe's evolution backward in time. Then they had to find ways to test their models against reality. The age of the universe is not a guess or a rough estimate. It's one of the most rigorously tested numbers in all of science, confirmed through multiple independent methods. Yet it's also at the center of one of the hottest debates in modern physics. This combination, solid knowledge resting atop profound mystery, is typical of cutting-edge science. We know things with great precision while simultaneously discovering how much we still don't know. As you continue to relax, breathing slowly and deeply, consider what it means that the universe has an age at all. It means there was a beginning. It means everything around us, matter and energy and space itself, came into existence at a specific moment in time. Before that moment, there was no space, no time, no matter, no energy, no anything. Not darkness, not emptiness, not void. Nothing. And then, In an instant that defies imagination, everything began. This realization represents one of the most profound shifts in human understanding. For most of history, philosophers and theologians debated whether the universe was created or eternal. Some believed in a moment of creation. Others insisted the cosmos had always existed and always would. The question seemed beyond the reach of science, a matter of faith rather than evidence. Yet here we are, able to state with confidence based on multiple lines of observational evidence that the universe is finite in age, that it had a beginning we can date with remarkable precision. The journey to this knowledge spanned decades and required contributions from hundreds of scientists across multiple disciplines. Observational astronomers measured the distances and velocities of galaxies. Theoretical physicists developed models of how the universe evolves. Particle physicists explored the behavior of matter under extreme conditions. Radio astronomers discovered the cosmic microwave background. Satellite missions mapped this ancient radiation in exquisite detail. Each piece of evidence fit together like parts of an enormous puzzle, revealing a consistent picture of a universe born nearly 14 billion years ago. Think about what this means for the oldest objects we can observe. The most ancient stars in our galaxy, found in globular clusters orbiting in the galactic halo, are approximately 12 to 13 billion years old. These stellar elders formed when the universe itself was less than a billion years old. They've witnessed most of cosmic history, slowly consuming their nuclear fuel while galaxies formed, collided, and evolved around them. Some of these stars are so old that they contain almost no elements heavier than helium, because they formed before enough generations of stars had lived and died to significantly enrich the cosmos with heavier elements. The precision with which we can measure the universe's age represents an extraordinary achievement. Consider the challenges involved. We can't observe the entire universe, only the portion whose light has had time to reach us. We can't directly see the universe as it was moments after the Big Bang. We can only infer conditions from the evidence that survives. We're trying to reconstruct 13.8 billion years of history from observations made in the present, like archaeologists piecing together ancient civilizations from fragments and ruins. Yet we've succeeded. Through careful observation, rigorous analysis, and sophisticated modeling, we've determined when the universe began to within less than 1% uncertainty. This ranks among humanity's greatest intellectual achievements, on par with understanding DNA's structure, discovering the fundamental particles and forces of nature, or mapping the human genome. We've answered one of the oldest and deepest questions our species has ever asked. Measuring the cosmic clock. How do you measure the age of something as vast as the universe? You can't exactly count rings on a cosmic tree or use carbon dating on the fabric of space itself. Scientists had to develop entirely new methods, ingenious ways of reading time in the structure of reality itself. The answer came from an unexpected place. A faint hiss of radio static that two scientists accidentally discovered while trying to eliminate noise from a satellite antenna. In 1964, Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey, trying to build a very sensitive radio receiver for satellite communications. They kept detecting an annoying background noise that wouldn't go away. They cleaned pigeon droppings out of the antenna. They pointed the antenna in different directions. Nothing worked. The noise remained, constant and unchanging, coming from every direction in the sky. What they had stumbled upon was one of the most important discoveries in the history of astronomy: the cosmic microwave background radiation. This faint glow fills the entire universe, a fossil remnant of the Big Bang itself. It's the oldest light in the universe, released when the cosmos was just 380,000 years old. And embedded in its subtle variations are clues to the universe's age, composition, and evolution. Let your eyes grow heavy as you imagine this ancient light. The cosmic microwave background was released at a specific moment in the early universe, a moment called recombination. Before this moment, the universe was so hot and dense that matter existed as a soup of charged particles, protons and electrons flying freely. Light couldn't travel far before being absorbed or scattered by these charged particles. The universe was opaque, like being inside a thick fog, but as the universe expanded, it cooled. Eventually, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the universe became transparent. Light that had been trapped, constantly scattering off charged particles, was suddenly free to travel. This light has been traveling ever since, for more than 13 billion years, growing cooler and more stretched out as the universe itself expanded. Today, that light has cooled to a temperature of just 2.725 degrees above absolute zero, where all motion stops. It's so cool that it's no longer visible light. It's microwave radiation, invisible to our eyes but detectable with sensitive instruments. The cosmic microwave background has almost exactly the spectrum predicted for something called blackbody radiation, thermal radiation from an object in perfect equilibrium. This perfect match to theory was one of the strongest confirmations of the Big Bang model. But the cosmic microwave background isn't perfectly uniform. It has tiny temperature variations, hot spots and cold spots that differ from the average by only a few hundred thousandths of a degree. These variations might seem insignificant, but they're actually tremendously important. They represent the seeds of all structure in the universe. Regions that were slightly denser than average eventually collapsed under their own gravity to form the first stars and galaxies. The pattern of these variations contains a wealth of information. By analyzing them in detail, scientists can determine the universe's composition, its geometry, its rate of expansion, and crucially, its age. The first detailed map of these variations came from NASA's Cosmic Background Explorer satellite, COBE, launched in 1989. The COBE results earned its principal scientists, John Mather and George Smoot, the Nobel Prize in Physics in 2006. Even more detailed measurements came from COBE's successor, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. WMAP measured the cosmic microwave background with unprecedented precision, creating a map that showed the universe as it appeared 380,000 years after the Big Bang. From this baby picture of the cosmos, scientists could extract fundamental parameters describing the universe's properties. MAP's measurements were revolutionary. They determined that the universe is 13.77 billion years old, with an uncertainty of only about 140 million years. They showed that ordinary matter, the stuff that makes up stars and planets and people, accounts for only about 4.6% of the universe's total energy. About 22.8% is dark matter, invisible material that interacts only through gravity. And a whopping 72.6% is dark energy, a mysterious force driving the universe's accelerating expansion. But scientists didn't stop there. The European Space Agency's Planck satellite, launched in 2009, measured the cosmic microwave background with even greater precision. Planck could detect temperature variations as small as a few millionths of a degree. Its final results, published in 2018, refined the age of the universe to 13.787 billion years, plus or minus 20 million years. Feel your body sinking deeper into relaxation as you contemplate these measurements. Imagine the cosmic microwave background surrounding you, this ancient light that has traveled for more than 13 billion years to reach your location in space. Every cubic centimeter of the universe is filled with about 400 photons of this radiation. Right now, as you rest here, hundreds of billions of these ancient particles of light are passing through your body every second, ghosts from the birth of time itself. The cosmic microwave background also revealed the geometry of the universe. The sizes of the hot and cold spots in the background radiation depend on the curvature of space. If space is curved like the surface of a sphere, the spots would appear larger. If curved like a saddle, they'd appear smaller. Planck's measurements showed that space is flat, or very nearly so. The universe has zero curvature, at least on the largest scales we can measure. This flatness was predicted by inflation theory, which proposes that the universe underwent a period of exponential expansion in the first tiny fraction of a second after the Big Bang. During this inflation, any initial curvature would have been stretched out, like how the surface of a balloon appears flatter as you inflate it. The cosmic microwave background provides strong support for inflation, showing a pattern of variations consistent with quantum fluctuations magnified to cosmic scales. Imagine the cosmic microwave background as a three-dimensional sphere surrounding Earth, located at the point where light was released when the universe became transparent. This sphere has a radius of about 13.8 billion light-years in all directions. It's the farthest we can possibly see using electromagnetic radiation. Before the moment of recombination, the universe was opaque, so we can never directly observe earlier times with light. The cosmic microwave background is our ultimate horizon, the oldest light we can ever detect. The patterns in this ancient light are remarkably informative. Sound waves propagating through the hot plasma before recombination left their imprint as variations in temperature. These acoustic oscillations had a characteristic scale determined by how far sound could travel in the 380,000 years before recombination. This scale shows up clearly in the statistics of the cosmic microwave background, appearing as a series of peaks in what's called the power spectrum. By analyzing these peaks, cosmologists can determine the universe's fundamental parameters with extraordinary precision. The height and positions of different peaks reveal the densities of ordinary matter, and dark energy. They tell us the universe's expansion rate at different epochs. They constrain the total energy density of the universe. They even provide information about the physics of the very early universe, potentially offering clues about conditions during the inflationary epoch. The cosmic microwave background has another remarkable property. It's almost perfectly uniform. After accounting for the motion of our solar system through space, which creates a dipole pattern as we move towards some regions and away from others, the temperature is the same in all directions to within about 1 part in 100,000. This extraordinary uniformity posed a puzzle that inflation theory elegantly solved. Without inflation, Regions of the universe on opposite sides of the sky would never have been in causal contact, never had time to exchange information or equalize their temperatures. Yet they have almost exactly the same temperature. Inflation explains this by proposing that these now distant regions were once close together in thermal equilibrium before inflation stretched them apart. The precision of these measurements is staggering when you think about it. Scientists can look at the pattern of ancient light, run it through complex models of cosmology and physics, and extract not just the age of the universe but its entire composition and history. They can tell you what the universe was made of 13.8 billion years ago, how fast it was expanding, how matter was distributed, and how it evolved to its current state. Other methods of dating the universe provide independent confirmation. Astronomers can estimate the ages of the oldest stars in globular clusters, dense balls of ancient stars that orbit our galaxy. These calculations, based on models of stellar evolution, suggest ages of around 12 to 13 billion years for the oldest stars. This is perfectly consistent with a universe that's 13.8 billion years old, since the stars couldn't have formed until after the universe itself existed for some time. The radioactive dating of the oldest rocks in our solar system provides another check. These rocks formed about 4.5 billion years ago, when the solar system was young. Working backward, we can estimate when the first generation of stars must have formed to create the heavy elements found in these rocks. All the evidence points to the same conclusion. The universe is approaching its 14th billionth birthday. As you drift closer to sleep, let this knowledge settle over you like a warm blanket. The universe is 13.8 billion years old. Scientists know this with extraordinary precision, having measured it multiple independent ways. Every method points to the same answer, the same moment of beginning, the same cosmic clock ticking away since time itself began. The Hubble constant controversy. But here's where the story takes an intriguing turn, one that might pique your interest even as sleep calls to you. While the cosmic microwave background gives us one answer for the universe's age, other measurement methods are producing slightly different results. This disagreement has evolved from a minor discrepancy into what cosmologists now call the Hubble tension, and it may be pointing toward revolutionary new physics. The Hubble constant is named for Edwin Hubble, who in 1929 made one of the most profound discoveries in the history of astronomy. He found that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship between distance and velocity revealed that the universe itself is expanding, with space stretching like the surface of an inflating balloon. Imagine a raisin bread dough rising in the oven. As the dough expands, every raisin moves away from every other raisin. A raisin twice as far away will move twice as fast, not because it's traveling through the dough faster, but because there's more expanding dough between them. This is precisely how the universe works, except instead of raisins we have galaxies, and instead of dough we have space itself. The Hubble constant measures the rate of this expansion. It tells us how fast space is stretching. Specifically, it gives the velocity at which galaxies are receding per unit distance. The current best estimates put it at around 67 to 73 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light-years, the recessional velocity increases by 67 to 73 kilometers per second. Why does this matter for the age of the universe? Because if you know how fast the universe is expanding now, you can work backwards to figure out when everything must have been in the same place. If the expansion rate has been constant, the age would simply be 1 divided by the Hubble constant. But the expansion hasn't been constant. Gravity has been slowing it down for most of cosmic history, and dark energy has been speeding it up more recently. Still, the Hubble constant is crucial for calculating the universe's age. And this is where the problem arises. Different methods of measuring the Hubble constant give different answers. The cosmic microwave background method, which uses observations of the early universe combined with models of cosmology, consistently gives a value around 67.4 kilometers per second per megaparsec. This would correspond to a universe about 13.8 billion years old. But measurements based on observations of the nearby universe, using a technique called the cosmic distance ladder, give higher values, typically around 73 to 74 kilometers per second per megaparsec. If this higher value is correct, the universe would be somewhat younger, perhaps closer to 12.8 to 13.2 billion years old. The difference might not sound huge, but in cosmology it's enormous. Let your breathing slow as we explore why this matters. The cosmic distance ladder is a clever method that builds up distance measurements step by step, each step calibrated by the previous one. The first rung uses nearby stars whose distances can be measured directly through parallax, the apparent shift in position when viewed from different points in Earth's orbit. The second rung uses Cepheid variable stars, whose intrinsic brightness is related to how quickly they pulsate. By measuring how bright they appear and knowing how bright they actually are, we can calculate their distance. The third rung uses type Ia supernovae, exploding white dwarf stars that reach almost the same peak brightness each time. These are bright enough to be seen in distant galaxies, allowing distance measurements across billions of light years. By combining all these rungs, astronomers can measure distances to galaxies far across the universe and determine how fast they're moving away. This gives a direct measurement of the Hubble constant in the present-day universe. This method has been refined over decades by teams led by astronomers like Adam Rees of Johns Hopkins University and Wendy Friedman of the University of Chicago. The Hubble Space Telescope played a crucial role, allowing precise measurements of Cepheid variables in distant galaxies. More recently, the James Webb Space Telescope has provided even sharper observations, confirming the Hubble measurements with unprecedented clarity. And yet, the discrepancy persists. The early universe method says 67.4. The late universe method says 73 to 74. These measurements are now precise enough that the disagreement is statistically significant. It's not just measurement error or bad luck. Something interesting is going on. This is the Hubble tension, and it's become one of the most pressing puzzles in cosmology. Some researchers have suggested it might indicate problems with the cosmic distance ladder. Maybe there are subtle systematic errors in how we calibrate Cepheid variables. Maybe type Ia supernovae aren't quite as standard as we thought. Maybe local gravitational effects are biasing the measurements. But the measurements have been checked and rechecked. Different teams using different methods arrive at similar results. The James Webb Space Telescope observations have eliminated many potential sources of error. If there's a flaw in the cosmic distance ladder, it's remarkably well hidden. The alternative is more exciting. Maybe the universe is telling us something new. Maybe our standard model of cosmology, called lambda CDM, is missing something important. Lambda represents dark energy, the mysterious force driving the universe's accelerating expansion. CDM stands for cold dark matter, the invisible substance that makes up most of the matter in the universe. This model has been extraordinarily successful, matching observations from the cosmic microwave background, galaxy surveys, and gravitational lensing. But maybe it's not the complete picture. One possibility is that dark energy isn't constant. Recent data from the Dark Energy Spectroscopic Instrument, or DESI, hints that dark energy's strength may have changed over cosmic history. If dark energy was weaker in the past and stronger now, it would affect the universe's expansion history in ways that could resolve the Hubble tension. But this would be revolutionary, requiring us to rethink fundamental assumptions about the nature of dark energy. Another possibility involves new particles or forces that we haven't discovered yet. Some theories propose additional types of neutrinos or other exotic particles that would affect the early universe's expansion rate. Others suggest modifications to general relativity itself, Einstein's theory of gravity that underlies our understanding of cosmology. These ideas are speculative, but the Hubble tension is forcing cosmologists to consider them seriously. Feel yourself drifting as you contemplate this mystery. The universe might be 13.8 billion years old, or it might be somewhat younger. We might be on the verge of discovering new physics, or we might simply need to refine our measurements further. Either outcome would be fascinating. Science thrives on such tensions, where careful observations reveal something that doesn't quite fit our theories. Recent work has added new dimensions to this puzzle. In January 2025, a team led by Dan Skolnick at Duke University published measurements giving a Hubble constant of 76.5 kilometers per second per megaparsec, even higher than previous estimates. They called it a crisis, saying the tension has now turned into something that demands explanation. The discrepancy is too large, too persistent, and too well measured to dismiss. Meanwhile, the Atacama Cosmology Telescope in Chile, which also measures the cosmic microwave background, has produced results that agree with Planck's measurements. The early universe method keeps giving answers around 67, while the late universe method keeps giving answers in the low to mid-70s. The gap isn't closing. What makes this particularly intriguing is that both methods should work. The cosmic microwave background is well understood physics. We know how radiation behaves, how atoms form, how sound waves propagate through the early universe. The cosmic distance ladder is also based on solid physics. We understand how stars work, how supernovae explode, how light travels through space. Yet somehow, these two approaches are giving inconsistent answers. Some cosmologists think the resolution will come from better understanding of systematic uncertainties. Maybe there are subtle effects we haven't accounted for in how we measure distances to Cepheid variables. Maybe the distribution of matter in the universe affects our observations in unexpected ways. Maybe we need to recalibrate some step in the distance ladder. Others think we're seeing evidence of new physics. Maybe there was an early period of dark energy in the universe's history. Maybe dark matter interacts with other particles in ways we haven't detected. Maybe the universe's expansion is more complex than our models assume. Maybe gravity itself works differently on cosmic scales than we thought. As you settle into deeper relaxation, consider what it means that we can even have this debate. We live in an era where scientists can measure the universe's expansion rate to such precision that a few kilometers per second per megaparsec matters. We can look back 13 billion years and measure what the universe was like when it was just 380,000 years old. We can compare these measurements and find meaningful discrepancies that might lead to new discoveries. The Hubble tension is science at its best. Careful measurements, rigorous analysis, honest acknowledgement of uncertainty, and excitement about what we might learn from the disagreement. Whether it's resolved through better measurements or revolutionary new physics, the process of figuring it out will deepen our understanding of the cosmos. The Big Bang, the beginning of everything. To understand the universe's age, we need to understand its beginning. This takes us to the Big Bang, one of the most profound and often misunderstood concepts in all of science. Let your mind wander through these ideas. No need to grasp every detail. Just let the story of creation wash over you like a gentle tide. The Big Bang wasn't an explosion. This is perhaps the most common misconception. The name itself is misleading, conjuring images of matter and energy blasting outward from some central point into pre-existing space. But that's not what happened. The Big Bang was the beginning of space itself, the moment when distance and dimension came into existence. There was no center, no edge, no surrounding emptiness. Everything that exists was everywhere at once, compressed into an infinitesimally small, infinitely dense state. The term Big Bang was actually coined by Fred Hoyle, an astronomer who favored an alternative theory called the steady-state model. He meant it mockingly, trying to make the idea sound absurd. Instead, it stuck and became the name for the most successful cosmological theory ever developed. Hoyle himself eventually accepted much of the evidence for the Big Bang, though he never completely abandoned his skepticism. So what actually happened at the beginning? The honest answer is we don't know for certain. Our physics breaks down at the very first instant. We can describe the universe from about 10 to the minus 43 seconds after the Big Bang, a time called the Planck time, but before that, our current theories of physics simply don't apply. Gravity, space, time, and quantum mechanics all become hopelessly entangled in ways we can't yet describe mathematically. But from the Planck time onward, we can piece together the story. The universe was unimaginably hot and dense, filled with pure energy. The temperature was around 10 to the 32nd power degrees Celsius, so hot that the very concept of particles breaks down. All the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force were unified into a single force. As the universe expanded and cooled, these forces separated. First gravity split off, then the strong nuclear force, then the weak force and electromagnetism separated from each other. This happened in the first trillionth of a second. Let yourself relax into the impossibility of these timescales. A trillionth of a second is to a second what a second is to 30,000 years. And in these impossibly brief moments, the fundamental architecture of reality was established. During this early period, the universe may have undergone inflation, a period of exponential expansion far faster than the speed of light. This might sound like it violates Einstein's relativity, which says nothing can move faster than light, but it doesn't. Objects can't move through space faster than light, but space itself can expand at any rate. Inflation would have stretched the universe by an enormous factor in a tiny fraction of a second, smoothing out any initial irregularities and explaining why the universe looks so uniform on large scales. As the universe continued to expand and cool, matter began to form. First, quarks and other fundamental particles condensed out of the energy soup. Then, after about 1 microsecond, quarks combined to form protons and neutrons. This was still incredibly hot, around 10 trillion degrees, hotter than anything that exists in the universe today, even in the cores of the most massive stars. For the next few minutes, the universe underwent what's called Big Bang nucleosynthesis. Protons and neutrons collided and stuck together, forming the nuclei of the lightest elements. Mostly hydrogen, some helium, and traces of lithium. This process lasted only about 3 minutes. After that, the universe had expanded and cooled too much for nuclear fusion to continue. All the helium in the universe today, about 25% of ordinary matter by mass, was formed in those first 3 minutes. The rest is hydrogen with just traces of heavier elements. Then came a long period of waiting. The universe was filled with a hot plasma of nuclei and electrons, too hot for atoms to form. Light couldn't travel far because it kept scattering off the free electrons. The universe was opaque, like a thick fog. This continued for about 380,000 years, an enormously long time compared to what had come before, but still just a tiny fraction of the universe's total age. Finally, the universe cooled enough for electrons to combine with nuclei, forming the first neutral atoms, mostly hydrogen. This is the moment of recombination, when the cosmic microwave background was released. Suddenly, the universe became transparent. Light could travel freely for the first time. This light has been traveling ever since, redshifted and cooled by the universe's expansion, until it reaches our telescopes today as the faint microwave glow we discussed earlier. Feel your eyelids growing heavier as you imagine this ancient universe. After recombination, the cosmos entered what astronomers call the Dark Ages. There were no stars yet, no galaxies, just vast clouds of hydrogen and helium slowly collapsing under their own gravity. This period lasted for perhaps 100 million years, maybe longer. The universe was filled with neutral gas, cooling and clumping, preparing to ignite the first generation of stars. Those first stars were probably very different from the stars we see today. They formed from pure hydrogen and helium, with none of the heavier elements that later generations of stars would contain. This made them able to grow much larger than modern stars, perhaps hundreds of times the mass of our sun. These massive stars burned hot and bright, flooding the universe with ultraviolet light that began to ionize the hydrogen around them, creating bubbles of ionized gas that gradually grew and merged. This period, called reionization, transformed the universe from neutral to ionized over several 100 million years. The first galaxies were forming, small and irregular, nothing like the grand spirals and ellipticals we see in the nearby universe today. These baby galaxies collided and merged, building up larger structures. The first supermassive black holes formed, growing at the centers of young galaxies, feeding on gas and stars. About 1 billion years after the Big Bang, the universe was beginning to look more familiar. Galaxies were maturing, stars of different generations were forming and dying, heavy elements were being forged in stellar cores and scattered by supernova explosions. The cosmic web of dark matter was pulling ordinary matter into vast filaments and sheets, creating the large-scale structure we observe today. Our own Milky Way galaxy began to form around this time, though it was much smaller and messier than it is now. Over billions of years, it grew through mergers with other galaxies, gradually developing its elegant spiral structure. Our solar system wouldn't form until much later, about 9 billion years after the Big Bang, when the universe was already 65% of its current age. Let the weight of this history settle over you. Everything around you, every atom in your body, every particle of air you breathe, every photon of light you see, emerged from that primordial fireball 13.8 billion years ago. The carbon in your cells was forged in the cores of ancient stars that exploded long before the Earth existed. The iron in your blood was created in the violent death throes of massive stars, then scattered into space to be incorporated into new generations of planets and life. You are, quite literally, made of star stuff, as Carl Sagan famously said. Your atoms are older than the Earth, older than the Sun, nearly as old as the universe itself. They've been on an extraordinary journey through space and time, cycling through stars and nebulae, eventually coming together to form you. And now, for this brief moment in cosmic history, you have the privilege of consciousness, of being able to contemplate your own origins and the vast sweep of time that led to your existence. The expanding universe. The discovery that the universe is expanding ranks among the greatest revelations in human history. For thousands of years, people assumed the cosmos was static and eternal. Even Einstein, when he developed his general theory of relativity in 1915, added a term called the cosmological constant specifically to keep the universe from expanding or contracting in his equations. He later called this his greatest blunder, though interestingly, that term has returned in modified form as dark energy. Let yourself drift into comfortable drowsiness as we explore how this revolutionary discovery unfolded. In the early 20th century, astronomers were beginning to realize that some of the fuzzy patches of light visible through telescopes were actually distant galaxies, separate island universes beyond our own Milky Way. Henrietta Leavitt's work on variable stars provided a crucial tool for measuring cosmic distances, allowing astronomers to determine how far away these galaxies were. Meanwhile, Vesto Slipher was measuring the spectra of these galaxies and making a puzzling discovery. Most of them showed redshift, meaning their light was shifted toward longer, redder wavelengths. According to the Doppler effect, this meant they were moving away from us. By 1929, Edwin Hubble had combined Slipher's velocity measurements with distance measurements to make a remarkable discovery. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, revealed that the universe itself was expanding. Every galaxy is moving away from every other galaxy, not because they're traveling through space, but because space itself is stretching. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. That's what's happening to galaxies in our expanding universe. This discovery immediately suggested something profound. If the universe is expanding now, it must have been smaller in the past. Working backwards, there must have been a moment when everything was compressed together, infinitely dense and hot. This was the key evidence for the Big Bang theory, though it would take several more decades and additional discoveries to convince the scientific community. The expansion has continued for nearly 14 billion years, but it hasn't been uniform. In the early universe, gravity was working to slow the expansion. The universe was dense with matter, and all that matter was pulling on everything else through gravity, like a ball thrown upward that slows as Earth's gravity pulls it back down. Scientists expected that either the universe would eventually stop expanding and collapse back on itself, or it would expand forever but at an ever-decreasing rate. Then, in 1998, came another revolutionary discovery. Two independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, were using Type Ia supernovae to measure the universe's expansion history. These supernovae are remarkably consistent in brightness, making them excellent cosmic distance markers. What they found shocked everyone. The distant supernovae were dimmer than expected, meaning they were farther away than they should be if the expansion was slowing down. The universe's expansion wasn't decelerating, it was accelerating. Something was pushing space apart, overcoming gravity's attractive pull. This discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. This mysterious something is what we call dark energy. We don't know what it is. We don't know where it comes from. We don't know how it works. We just know it's there, making up about 68% of the total energy in the universe, driving space to expand faster and faster. Feel your breath slowing as you contemplate this mystery. Most of the universe is made of something we can't see, can't touch, can't detect except through its gravitational effects. Dark energy might be a property of space itself, a sort of background energy that becomes more important as the universe expands and matter dilutes. This is called the cosmological constant, Einstein's old term repurposed for a new phenomenon. If dark energy is the cosmological constant, it has a fixed density that doesn't change as the universe expands. As the volume of the universe increases, more dark energy appears, because every cubic meter of space contains the same amount of it. Alternatively, dark energy might be something more dynamic, a field that varies over space and time. Some theories propose quintessence, a hypothetical field that changes its strength as the universe evolves. Recent data from the Dark Energy Spectroscopic Instrument suggests that dark energy may not be constant, that its properties might be changing. If confirmed, this would be revolutionary, potentially requiring completely new physics. Whatever dark energy is, it dominates the universe's fate. If dark energy remains constant, the universe will continue expanding forever, getting larger, colder, and emptier. Galaxies will drift apart until they can no longer see each other. Stars will burn out. Black holes will evaporate through Hawking radiation over timescales of 10 to the 100 years. Eventually, in the unimaginably distant future, the universe will approach what's called heat death, a state of maximum entropy where no energy is available to do work, and nothing can happen anymore. If dark energy grows stronger over time, the fate is even more dramatic. In a scenario called the Big Rip, dark energy's repulsive effect would eventually overcome all other forces. First, it would tear galaxy clusters apart, then individual galaxies, then solar systems, then planets, then molecules, then atoms, then atomic nuclei themselves. The universe would literally rip itself to shreds, space expanding so violently that nothing could hold together. This is speculative, but it's a real possibility that physicists take seriously. On the other hand, If dark energy is temporary or if it weakens over time, the universe might eventually stop accelerating. Gravity might reassert itself. The expansion could slow, stop, and reverse, leading to the Big Crunch, where the universe collapses back to a singularity. Some speculative theories even suggest this could be followed by another Big Bang, an endless cycle of expansion and contraction, though there's currently no evidence for this. For now, all evidence points to eternal expansion. The acceleration that began about 5 billion years ago shows no signs of stopping. The universe will get bigger and bigger, colder and colder, until the last stars burn out in a few trillion years. This might sound depressing, but let it soothe you into sleep. The universe's ultimate fate is so far in the future that it's essentially abstract. For now, we live in a vibrant cosmos, full of stars and galaxies, with billions of years of interesting cosmic evolution still ahead. The expanding universe also teaches us something profound about time itself. When we look at distant galaxies, we're seeing them as they were in the past, because light takes time to travel across space. A galaxy 1 billion light-years away appears to us as it was 1 billion years ago. The most distant galaxies visible to the James Webb Space Telescope appear as they were more than 13 billion years ago, when the universe was young. This means we can actually watch cosmic history unfold by observing galaxies at different distances. Nearby galaxies show us the recent past. More distant galaxies show us the more remote past. The most distant galaxies show us the early universe, when the first structures were forming. We can trace the evolution of galaxies, the changing rate of star formation, the assembly of large-scale structure, all by looking deeper into space and therefore further back in time. As you drift toward sleep, imagine this four-dimensional picture of the cosmos. Space and time are woven together, and every direction we look, we see a different moment in cosmic history. The universe is not just expanding in space, but unfolding in time, with its past written in the light of distant galaxies and its future hidden beyond the horizon of what we can observe. Early galaxy formation. The earliest chapters of cosmic history have long been hidden from us. The first stars and galaxies formed in an era so distant that their light has been traveling toward us for over 13 billion years. Until recently, these primordial structures remained largely theoretical, inferred from models but never directly observed. The James Webb Space Telescope has changed that, pulling back the curtain on the universe's infancy and revealing surprises that are forcing astronomers to reconsider their theories. Let your mind wander through this story of discovery. The first stars probably formed about 100 to 200 million years after the Big Bang, condensing from clouds of pristine hydrogen and helium that had never been touched by nuclear fusion. These population 3 stars, as astronomers call them, would have been massive, perhaps hundreds of times the mass of our Sun, burning fiercely hot and bright. Unlike modern stars, which contain a sprinkling of heavier elements forged in previous generations, these first stars were chemically pure. This allowed them to grow much larger than stars today possibly can. They lived fast and died young, burning through their nuclear fuel in only a few million years before exploding as supernovae. These explosions scattered the first heavy elements into space: carbon, oxygen, iron, and others, the seeds of future planets and life. These first stars probably didn't exist in isolation. They formed in small protogalaxies, clumps of dark matter that had attracted enough normal matter to begin forming stars. Dark matter, which doesn't interact with light but exerts gravitational pull, created the scaffolding on which the visible universe built itself. Its gravity pulled ordinary matter into dense regions where stars could form. Feel yourself relaxing deeper as you picture these baby galaxies. They were small and irregular, nothing like the majestic spirals and ellipticals we see in the nearby universe. They were chaotic, turbulent, constantly merging with other proto-galaxies. Star formation happened in violent bursts, not the steady process we observe in mature galaxies. Supernovae exploded frequently, stirring up the gas and triggering new waves of star formation. The James Webb Space Telescope has now given us our first clear views of this era. Webb can see infrared light, which is crucial because the light from these distant galaxies has been stretched to longer wavelengths by the universe's expansion. What left these galaxies as visible or ultraviolet light arrives at Earth as infrared radiation, invisible to our eyes but perfectly suited to Webb's instruments. What Webb is finding is surprising astronomers. Galaxies in the early universe appear brighter and more numerous than expected. Some are more massive and well-organized than theory predicted. The universe seems to have gotten busy making galaxies earlier and more efficiently than cosmologists thought possible. This doesn't overturn the Big Bang theory or suggest the universe is older than we thought, but it does mean our models of galaxy formation need adjustment. One particularly surprising discovery involves galaxy mergers. Traditional theory suggested that in the very early universe, galaxies would typically merge in pairs or small groups. But Webb has discovered what astronomers call JWST's quintet, a system of at least 5 galaxies merging together when the universe was only 800 million years old. This kind of complex merger was thought to be rare or impossible so early in cosmic history. Even more intriguing, this merging system shows an extended halo of oxygen-rich gas surrounding the galaxies. Oxygen is a heavy element, forged in stars and expelled during supernovae. Finding so much oxygen so far from the galaxies themselves so early in cosmic history suggests that stars were forming, living, and dying even earlier than we realized, and that their explosions were distributing heavy elements across vast regions of space. Let your breathing slow as we explore more of what Webb has revealed. Some early galaxies appear to be feeding on streams of cold gas falling in from the surrounding intergalactic medium. This gas, still mostly hydrogen and helium from the Big Bang, provides the raw material for new star formation. Webb's spectra show the distinctive signatures of this pristine gas, almost completely devoid of heavy elements, the cosmic equivalent of looking at ingredients that haven't been cooked yet. Other observations show early galaxies surrounded by bubbles of ionized gas. These bubbles were carved out by intense ultraviolet radiation from young stars, which stripped electrons from hydrogen atoms, making the gas transparent to light. Over time, these bubbles grew and merged, eventually reionizing all the hydrogen in the universe. Webb is watching this reionization process in action, seeing how individual galaxies transformed their surroundings. The telescope has also revealed that early galaxies were much more chaotic and turbulent than their modern descendants. A study of over 250 young galaxies, existing when the universe was between 800 million and 1.5 billion years old, found that most were clumpy and irregular. Gas within these galaxies moved chaotically, stirred up by intense star formation and frequent supernova explosions. They hadn't yet settled into the smooth rotating disks characteristic of mature spiral galaxies like the Milky Way. This makes sense when you think about it. These galaxies were still in the process of assembling. They were constantly being bombarded by fresh gas from the intergalactic medium, constantly merging with other galaxies, constantly experiencing bursts of star formation. It took time for them to calm down, for their stars to settle into orderly orbits, for the turbulence to dissipate. The early universe was a violent, chaotic place. Webb has also spotted unexpected features in some early galaxies. One galaxy, observed just 330 million years after the Big Bang, shows bright hydrogen emission that should have been absorbed by the fog of neutral hydrogen filling the universe at that time. Somehow, this galaxy managed to create a clear bubble around itself far sooner than thought possible, allowing its light to escape and reach us. As you drift toward sleep, consider what these discoveries mean. The early universe was more complex, more active, more surprising than our models predicted. Galaxies formed earlier, grew faster, and evolved more rapidly than we expected. This doesn't mean our fundamental understanding is wrong, but it does mean the details are richer and more nuanced than we realized. Webb has also discovered surprisingly massive black holes in the early universe. These supermassive black holes, millions or even billions of times the mass of the Sun, sit at the centers of young galaxies. How they grew so large so quickly is a mystery. There simply wasn't enough time in the early universe for them to grow from stellar mass black holes through normal accretion of matter. Either they formed directly from the collapse of massive clouds of gas, or they grew through some process we don't yet understand. These discoveries highlight both how much we've learned and how much we still don't know. We can see galaxies as they appeared just a few 100 million years after the Big Bang. We can measure their properties, determine their ages, analyze their chemical composition. But we're still working out exactly how they formed, how quickly they grew, how they influenced each other and their surroundings. The first billion years of cosmic history are coming into focus, but they're revealing a universe more dynamic and surprising than we imagined. Every new observation raises new questions. Why are early galaxies brighter than expected? How did massive black holes form so quickly? What triggered the rapid star formation we observe? How did galaxies transition from chaotic clumps to orderly spirals? These questions will keep astronomers busy for years to come. Webb will continue observing, building up a statistical sample of early galaxies large enough to test different theoretical models. Other telescopes will contribute complementary observations. Theorists will refine their computer simulations, trying to reproduce what Webb is seeing. Gradually, a clearer picture will emerge of how the universe evolved from the smooth plasma of the cosmic microwave background to the rich structure we see today. Dark matter and dark energy. As you settle into deeper relaxation, let's explore perhaps the most profound mystery in modern cosmology. Most of the universe is invisible. When astronomers tally up all the ordinary matter they can see, all the stars and gas and dust, it accounts for less than 5% of the total energy in the universe. The rest is dark matter and dark energy, substances or forces we've never directly detected, but whose effects shape everything we observe. Dark matter was discovered through its gravitational influence on visible matter. In the 1930s, Astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving faster than they should if only visible matter was present. The cluster didn't contain enough luminous matter to gravitationally bind the galaxies together at their observed speeds. Either galaxies were flying apart, which they clearly weren't, or there was additional mass we couldn't see. This observation was largely ignored for decades. Then, in the 1970s, Vera Rubin made detailed measurements of how stars orbit in spiral galaxies. She found that stars far from a galaxy center moved just as fast as stars closer in. This was unexpected. If most of a galaxy's mass was concentrated in its visible disk, stars farther out should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But they didn't. The rotation curves stayed flat instead of declining. This meant galaxies contained vast halos of invisible matter extending far beyond their visible edges. This dark matter doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all. We know it's there only through its gravitational effects. Feel your muscles loosening as you contemplate this invisible universe. Dark matter makes up about 27% of the total energy in the cosmos. It forms the cosmic skeleton on which visible structure hangs. Computer simulations show that without dark matter, galaxies as we know them couldn't form. There wouldn't be enough gravitational pull to collect gas into dense regions where stars could ignite. What is dark matter made of? Nobody knows for certain. It's not ordinary matter like protons, neutrons, and electrons. Those particles interact with light. Dark matter must be something else, perhaps exotic particles predicted by theories extending beyond the standard model of particle physics. Leading candidates include WIMPs, weakly interacting massive particles, and axions, extremely light particles that would exist in enormous numbers. Despite decades of searching, no one has directly detected dark matter particles. Experiments deep underground wait patiently for a dark matter particle to collide with ordinary matter, but so far, nothing. The Large Hadron Collider has tried to create dark matter particles in high-energy collisions, but hasn't succeeded. Either dark matter is even harder to detect than we thought, or we're looking in the wrong place, or it's not particles at all but something stranger. Some physicists have proposed alternatives. Maybe there's no dark matter, and instead gravity works differently on large scales than Einstein's general relativity predicts. These modified Newtonian dynamics theories, or MOND, can explain some observations but struggle to match others. The cosmic microwave background and galaxy cluster collisions strongly favor dark matter over MOND. Most physicists believe dark matter is real, even if we haven't found it yet. Dark energy is even more mysterious. We discovered it only in 1998, when observations of distant supernovae revealed that the universe's expansion is accelerating. Something is pushing space apart, overcoming gravity's attractive pull. This something is dark energy, and it makes up about 68% of the universe's total energy. Dark energy behaves very differently from ordinary matter or dark matter. Matter clusters together under gravity, forming stars and galaxies. Dark energy is smooth and uniform, filling all of space evenly. It doesn't clump or cluster. Its density remains constant even as the universe expands, which seems to violate conservation of energy until you remember that in general relativity, space itself has energy. The simplest explanation for dark energy is that it's a cosmological constant, a property of empty space itself. In quantum field theory, even vacuum contains energy due to quantum fluctuations. Particles and antiparticles constantly pop into and out of existence. This vacuum energy could be what we observe as dark energy. The problem is, when physicists calculate how much vacuum energy there should be, they get an answer that's 10 to the 120th power times larger than what we observe. That's 1 followed by 120 zeros. It's one of the worst predictions in the history of physics. This enormous discrepancy is called the cosmological constant problem, and nobody knows how to solve it. Why is vacuum energy so much smaller than theory predicts? Why does it have exactly the right value to become important just recently in cosmic history? These are deep questions touching on the fundamental nature of quantum mechanics and gravity. Let yourself sink into comfort as your mind drifts through these ideas. Recent observations hint that dark energy might not be constant. The Dark Energy Spectroscopic Instrument has collected data on millions of galaxies, mapping how the universe's expansion has changed over time. Their preliminary results suggest dark energy's properties may have evolved, being weaker in the past and stronger now. If confirmed, this would be revolutionary. It would mean dark energy isn't Einstein's cosmological constant, but something more dynamic. Perhaps it's a field permeating space, similar to the Higgs field that gives particles mass. This hypothetical quintessence field could vary in strength over cosmic time, explaining why its effects are becoming dominant only now. Or perhaps dark energy is a sign that general relativity breaks down on cosmological scales. Einstein's theory works magnificently for describing gravity from planets to black holes, but maybe it's incomplete when applied to the entire universe. Some theories propose modifications to general relativity that would produce cosmic acceleration without requiring dark energy. These ideas are speculative, but the mysterious nature of dark energy is forcing physicists to consider them. Together, dark matter and dark energy present a humbling picture. We understand only about 5% of the universe directly. The rest is mystery. The stars and galaxies we see, everything we've ever observed with telescopes, all the matter on Earth and throughout the solar system, is just a small fraction of what exists. We're like people seeing the shadow of something vast, trying to deduce its nature from how it affects the small portion we can observe. This isn't a failure of science. It's a testament to science's power. We've discovered our own ignorance. We know that something we can't see is affecting the universe in measurable ways. We've mapped where dark matter is through gravitational lensing, watching how its gravity bends light from background galaxies. We've measured how dark energy has shaped the universe's expansion history. We've made testable predictions about how these invisible components should behave. As you drift closer to sleep, consider the profound strangeness of the universe we inhabit. Most of it is invisible to us. Its nature remains mysterious. And yet, through careful observation and rigorous thinking, we've learned it exists. We've measured its effects. We've constrained its properties. We're asking the right questions, even if we don't yet have all the answers. The search for dark matter continues in laboratories around the world. New experiments with greater sensitivity are being built. The hunt for dark energy drives new telescope surveys and space missions. Perhaps in your lifetime, someone will discover what these mysterious components actually are. Or perhaps the mystery will deepen, revealing even stranger aspects of reality we haven't imagined yet. Either way, the universe is far more interesting than it appears at first glance. Behind the familiar cosmos of stars and galaxies lies a hidden universe of invisible matter and mysterious energy. This shadow universe shapes everything we see, determines the universe's fate, and reminds us how much we still have to learn about the cosmos we call home. The universe today and tomorrow. As your breathing becomes slower and deeper, let's bring our journey through cosmic time to the present moment, and then peer tentatively into the future. The universe today is 13.8 billion years old, in the prime of its evolution, with trillions of years of interesting history still ahead before the last stars burn out and darkness finally claims the cosmos. The nature of cosmic time and space. Before we look to the future, let yourself sink deeper into relaxation as we explore something fundamental about the nature of time and space in an expanding universe. These concepts are subtle and strange, but understanding them enriches our appreciation of just how remarkable our cosmic situation truly is. When we say the universe is 13.8 billion years old, we're measuring time in a very specific way. We're using what cosmologists call cosmic time, the time measured by a clock that has been moving with the expansion of the universe since the Big Bang. This is the same time that would be measured by the cosmic microwave background photons as they traveled through space. It's the natural clock of the cosmos itself. But time in an expanding universe is more complex than this simple picture suggests. According to Einstein's general relativity, time and space are not separate entities, but are woven together into a four-dimensional fabric called space-time. The expansion of the universe is really the stretching of this space-time fabric. This has profound implications for how we think about cosmic history and our place in the universe. Consider a photon of light emitted by a distant galaxy when the universe was 1 billion years old. This light has been traveling for what we measure as 12.8 billion years to reach us. But from the photon's perspective, if photons had perspectives, no time has passed at all. Traveling at the speed of light, the photon experiences no passage of time. The moment of its emission and the moment of its absorption by a telescope on Earth are, for the photon, the same instant. This isn't just philosophical musing, it's a consequence of relativity. Time passes differently for observers moving at different speeds or experiencing different gravitational fields. In the early universe, when matter was much denser and moving at high velocities relative to the cosmic average, time would have passed at different rates in different regions. The cosmic time we measure is an average, smoothed over the entire observable universe. The observable universe itself is a fascinating concept worth exploring as you drift towards sleep. When we say the observable universe, we mean the region of space from which light has had time to reach us since the Big Bang. This forms a sphere around Earth with us at the center. But this doesn't mean we're at the center of the universe itself. Every point in the universe has its own observable universe, and these spheres overlap and shift depending on where you're observing from. The radius of the observable universe is not 13.8 billion light-years, as you might expect from the universe's age. It's actually about 46.5 billion light-years. How can light from something 46 billion light-years away have reached us if the universe is only 13.8 billion years old? The answer lies in the expansion of space itself. Imagine a photon emitted by a galaxy when the universe was very young. The galaxy might have been, say, 1 billion light-years away when the light was emitted. But in the time it took for that light to travel to us, the universe expanded. Space itself stretched, carrying that galaxy farther away. By the time the light reaches us, the galaxy is now much more than 1 billion light-years distant, having been carried away by cosmic expansion even as its light was traveling toward us. This creates some counterintuitive situations. There are galaxies we can see whose light has been traveling for over 13 billion years, but which are now more than 40 billion light-years away because of the expansion that has occurred during the light's journey. And there are galaxies beyond our cosmic horizon that are receding from us faster than light, not because they're moving through space faster than light, which would violate relativity, but because the space between us is expanding faster than light can traverse it. These ultra-distant galaxies are forever beyond our reach. We will never be able to see them or communicate with them. As the universe continues to expand and dark energy drives accelerating expansion, our cosmic horizon will actually shrink. Galaxies that we can see today will eventually cross this horizon and disappear from view, their light redshifted to infinite wavelengths, effectively becoming invisible. Let your mind relax as you contemplate these vast scales. The observable universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars. That's more stars than grains of sand on all of Earth's beaches combined. And yet, this observable universe represents only a fraction of the total universe. Beyond our cosmic horizon lie regions we can never observe, galaxies we'll never see, perhaps infinitely many of them if the universe is truly infinite in extent. Is the universe infinite? We don't know. The cosmic microwave background observations tell us that space is flat or very nearly so, and in standard cosmological models, a flat universe is infinite. But we can only measure the curvature within our observable region. The universe beyond our horizon could have different properties. It could curve back on itself at scales larger than we can observe, or it could truly be infinite, stretching endlessly in all directions. If the universe is infinite, that has extraordinary implications. An infinite universe would contain infinite matter and energy. It would contain infinitely many galaxies, infinitely many stars, infinitely many planets. And if the laws of physics and chemistry are the same everywhere, then in an infinite universe, every possible arrangement of matter would occur infinitely many times. There would be infinitely many planets identical to Earth, infinitely many versions of you reading these very words. This infinite replication is called the cosmological principle taken to its logical conclusion. The principle states that the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same everywhere and in all directions. If this is true globally, not just within our observable region, and if the universe is infinite, then every configuration of matter that's physically possible must occur somewhere, and in fact must occur infinitely many times. Most physicists don't worry too much about these infinite duplicates. They may exist, but they're beyond our ability to ever observe or interact with. They're fundamentally disconnected from us by the expansion of space. For all practical purposes, our observable universe is all that matters to us. But it's a thought-provoking consequence of our current understanding of cosmology. The age of the universe also relates intimately to another fundamental question. What is time? In our everyday experience, Time flows from past to future. We remember the past but not the future. We can influence the future but not the past. This directionality of time, called the arrow of time, seems fundamental to our existence. Yet the fundamental laws of physics, from Newton's mechanics to Einstein's relativity to quantum mechanics, are largely time-symmetric. They work equally well forward and backward in time. If you filmed a collision between two particles and played it backward, the reversed version would still obey all the laws of physics. So where does the arrow of time come from? The answer seems to lie in the second law of thermodynamics, which states that entropy, a measure of disorder, always increases over time in a closed system. The universe started in a state of extremely low entropy, with all its energy concentrated in an incredibly ordered initial condition. As it evolved, entropy increased. Stars formed and burned out. Ordered structures assembled and eventually decayed. The overall disorder of the universe grew. This increase in entropy gives time its direction. We remember the past because our brains store information, which is a low entropy state. We can influence the future but not the past because increasing entropy is easier than decreasing it. The arrow of time emerges from the fact that the universe began in a special, low entropy state and has been evolving toward higher entropy ever since. But this raises a deep question. Why did the universe start in such a low entropy state? The Big Bang was an incredibly ordered initial condition. All the matter and energy in the observable universe emerged from a tiny region, in a state of near-perfect uniformity except for tiny quantum fluctuations. This seems like an extraordinarily unlikely starting point. In most configurations, the universe would be much more disordered. This is called the initial conditions problem, and it's one of the deep mysteries of cosmology. Inflation provides a partial answer by showing how quantum fluctuations could produce the observed patterns we see. But it doesn't fully explain why the universe started inflating in the first place, or why it started in a state conducive to inflation. These remain open questions, hints that our understanding of the universe's beginning is still incomplete. As you drift deeper into comfortable drowsiness, consider how these questions connect to the universe's age. The fact that we can measure this age, that we can look back to the beginning and forward to the end, is itself remarkable. Time is not just a backdrop against which cosmic events occur. It's woven into the very fabric of reality, intimately connected with space, matter, energy, and the expansion of the universe itself. Right now, at this moment in cosmic time, we live in what astronomers call the stelliferous era, the age of stars. Galaxies continue to form new stars from clouds of gas and dust, though the rate of star formation has been declining for billions of years. The peak of cosmic star formation happened about 10 billion years ago, when the universe was about 3 billion years old. Since then, galaxies have been slowly running out of the raw material needed to make new stars. Our Milky Way galaxy continues to form several new stars each year. It's a mature spiral galaxy, its structure shaped by billions of years of evolution. About 4 billion years from now, it will collide and merge with the Andromeda Galaxy, our nearest large galactic neighbor. This merger will scramble both galaxies, eventually forming a giant elliptical galaxy that some astronomers have already nicknamed Milkomeda. Let your mind relax as you imagine this cosmic collision. Despite the violent name, it will be a gentle process on human timescales. Stars are so far apart that despite billions of stars in both galaxies, actual stellar collisions will be extremely rare. Instead, the galaxies will interpenetrate, their stars settling into new orbits in the merged structure. The night sky will be spectacular for any beings around to see it, filled with nebulae and newly forming stars as gas clouds collide and compress. But this is all in the relatively near future, cosmologically speaking. Looking farther ahead, the universe's fate is determined by dark energy. If dark energy remains constant, as current evidence suggests, the universe will continue expanding forever, and the expansion will keep accelerating. This has profound implications for the very distant future. Currently, we can see galaxies billions of light years away, but as the universe expands, more distant galaxies are receding from us faster than the speed of light. This doesn't violate relativity because it's space itself expanding, not the galaxies moving through space. Eventually, these galaxies cross what's called the cosmic event horizon. Their light can no longer reach us because space between us is expanding too fast. As dark energy drives the expansion to accelerate, this cosmic horizon shrinks. Distant galaxies disappear from view one by one. Eventually, only our local group of gravitationally bound galaxies will be visible. Then only the Milkomeda galaxy. Far future astronomers, if any exist, won't be able to see evidence for the Big Bang. The cosmic microwave background will have redshifted to invisibility. They'll live in an apparently static universe containing only their own galaxy, unaware of the vast cosmos beyond their horizon. Feel yourself drifting into deeper relaxation as we contemplate these vast timescales. In about 1 trillion years, star formation will essentially cease. The last stars will be small red dwarfs, dim and long-lived, burning their fuel so slowly they can shine for trillions of years. When they finally burn out, the universe will enter the degenerate era, where the only light comes from slowly cooling stellar remnants. White dwarfs, neutron stars, and brown dwarfs. Eventually, even these will fade to invisibility. Black holes will be the only active objects, slowly accreting any matter that passes too close. And even black holes aren't eternal. Through a process called Hawking radiation, they slowly evaporate, converting their mass to radiation over enormously long timescales. A black hole with the mass of the Sun would take 10 to the 67th power years to evaporate. Supermassive black holes at galaxy centers would take even longer. But eventually, even the largest black holes will evaporate. The universe will enter the dark era, containing only isolated particles, photons, and neutrinos, all separated by ever-increasing distances as space continues to expand. The temperature will approach absolute zero. Nothing will happen anywhere. The universe will be dark, cold, and empty. This fate sounds bleak, but let it comfort you as you drift towards sleep. It's so far in the future that it's essentially abstract. For now, we live in an amazing epoch, when the universe is full of stars and galaxies, when chemistry is possible, when life can exist. We're here in the golden age of the cosmos, when the universe is neither too young to have formed complex structures, nor too old to still be interesting. And there's beauty in understanding the full arc of cosmic time. The universe had a beginning. It will have an end, at least in any recognizable form. Between those bookends stretches an enormously long story of galaxies and stars, of chemistry and complexity, of structure and evolution. We're privileged to exist during the interesting chapters. Moreover, our knowledge of the universe's age and fate has been hard-won. Each discovery built on previous ones. Each measurement required extraordinary ingenuity and persistence. From Edwin Hubble measuring galaxy distances with primitive instruments to the James Webb Space Telescope peering back to the universe's first billion years, humanity has gradually decoded the cosmos. We've measured the age of everything that exists. We've traced the universe's history from the first fraction of a second to the present day. We've mapped its contents, discovering that most of it is invisible and mysterious. We've identified fundamental questions we don't yet know how to answer. This is science at its best: careful observation, rigorous analysis, honest acknowledgement of uncertainty, and excitement about the mysteries that remain. Our place in cosmic history. As you settle into final drowsiness, let's explore one more dimension of what it means to live in a universe 13.8 billion years old. Where do we fit in this vast cosmic story? What does it mean to exist at this particular moment in universal history? Humanity appeared very recently on the cosmic timeline. If we compressed the entire history of the universe into a single year, with the Big Bang happening at the first second of January 1st, the Earth wouldn't form until early September. The first simple life would appear later that month. The dinosaurs would arise in late December and go extinct on December 30th. Modern humans wouldn't appear until the last few minutes of December 31st. All of recorded human civilization would fit into the final few seconds before midnight. This comparison highlights how brief our existence has been compared to the universe's total age. Yet, in another sense, we've arrived at a remarkably interesting time. The universe is neither too young nor too old for life to exist. Let yourself relax as you consider why this particular epoch is so special. In the very early universe, life would have been impossible. Temperatures were too high. There were no stable atoms, let alone molecules. There were no stars or planets. The chemistry necessary for life couldn't exist. We needed to wait for the universe to cool, for the first stars to form and create heavy elements, for those elements to be scattered by supernova explosions, for new generations of stars with planets to form from this enriched material. This process took billions of years. The first generation of stars contained only hydrogen and helium. They couldn't have planets like Earth. The second generation might have had some heavy elements, but probably not enough to form rocky planets with the right chemistry for life. Perhaps only by the third or fourth generation of stars did conditions become favorable for life as we know it. Our Sun is a relatively young star, only about 4.6 billion years old. It formed from a cloud enriched by many previous generations of stars. The Earth formed shortly afterward, and life appeared on its surface within the first billion years. In cosmic terms, we're relative newcomers. There may be civilizations in the galaxy far older than ours, unless we're among the first intelligent species to arise, an intriguing possibility sometimes called the early Earth hypothesis. But we also don't live too late. Imagine if humanity had appeared 1 trillion years from now, when the last stars were dying. We would inhabit a cold, dark universe with few opportunities for astronomy or cosmology. We wouldn't be able to see distant galaxies or measure cosmic expansion. We wouldn't have access to the cosmic microwave background, which would have cooled to invisibility. We might never discover that the universe had a beginning or learn anything about its early history. In a real sense, we live at a privileged time. The universe is still full of stars and galaxies. The cosmic microwave background is still detectable. Distant galaxies are still visible, allowing us to measure the expansion. We have access to the full range of evidence needed to decode cosmic history. We can look back to the beginning and forward to the end. Future civilizations, if any exist, won't have this opportunity. This realization adds poignancy to our cosmic situation. We're here, now, able to observe and understand the universe in ways that won't be possible in the far future. This makes our scientific explorations not just interesting but urgent. The knowledge we're gaining about cosmic origins and evolution is time-limited. In a sense, we're reading a book that will slowly fade, its pages becoming blank as dark energy pushes distant galaxies beyond our horizon and the cosmic microwave background cools to undetectability. Let your breathing slow as you think about the improbability of your existence. Every atom in your body was forged in a star or in the Big Bang itself. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created through nuclear fusion in stellar cores or supernova explosions. These atoms have been recycled through multiple generations of stars and interstellar clouds before eventually coming together to form you. The odds of any particular arrangement of atoms existing are astronomically small. And yet here you are, conscious and aware, able to contemplate the universe that made you. You're a rare and beautiful arrangement of matter that has achieved self-awareness, able to trace its own origins back through billions of years of cosmic evolution. Your atoms are ancient, nearly as old as the universe itself. But the specific pattern they form, the unique individual that is you, is temporary. After your death, these atoms will be returned to the earth, eventually to be recycled again. Some might become part of other living things. Some might drift into space. Given enough time, perhaps trillions of years, they might even be incorporated into new stars, completing a full cosmic cycle. This perspective can be simultaneously humbling and empowering. We're insignificant on cosmic scales, tiny specks of organized matter in a vast universe that would barely notice if Earth disappeared tomorrow. Yet we're also remarkable. We're the universe's way of knowing itself. Through our observations and theories, the cosmos has become aware of its own existence, its own history, its own eventual fate. Carl Sagan expressed this beautifully in the original Cosmos series. We are a way for the cosmos to know itself. Every scientific discovery, every measurement of cosmic parameters, every insight into how the universe works represents a moment when matter organized into human brains successfully decodes the larger reality it's embedded within. This is extraordinary when you think about it. The universe has existed for 13.8 billion years, but only very recently has any part of it become conscious and contemplative. As far as we know, intelligent life might be rare in the universe. Despite decades of searching, we haven't detected any signals from extraterrestrial civilizations. The Fermi paradox asks why, if the universe is so vast and old, we don't see evidence of other technological species. Perhaps life is common, but intelligence is rare. Perhaps intelligence is common, but technological civilizations are short-lived. Perhaps the distances between stars are simply too vast for easy communication. Or perhaps we're among the first. Perhaps the universe needed to age to this particular epoch before the conditions were right for complex life and intelligence to arise. If so, we're pioneers, the first wave of consciousness in a cosmos that's still very young compared to its total lifespan. Future epochs might see intelligence become common, civilizations spanning galaxies, minds far beyond our current capabilities. We might be the precursors to something grander, the first tentative steps of the universe toward full self-awareness. These are, of course, speculations. We don't know if we're alone or one of many. We don't know if intelligence is a common outcome of cosmic evolution or a rare accident. We don't know if civilizations typically survive long enough to spread among the stars or typically destroy themselves. But what we do know is that we're here now, in this particular moment of cosmic time, able to observe and understand our universe in unprecedented detail. This knowledge brings responsibility. We're the universe's witnesses, possibly its only current witnesses. We have a duty to observe carefully, to think clearly, to preserve and extend the knowledge we gain. Every telescope we build, every mission we launch, every experiment we conduct adds to humanity's collective understanding of the cosmos. This understanding is precious, hard-won through centuries of patient effort. Feel yourself sinking into final relaxation as you contemplate your cosmic heritage. You're made of stars. You're the product of 13.8 billion years of evolution, from the first quantum fluctuations in the early universe to the complex chemistry of living cells to the emergence of consciousness. The fact that you exist, that you can contemplate your own existence and place in the cosmos, is itself remarkable. Sleep now with the knowledge that you're part of something vast and ancient. The atoms in your body have witnessed cosmic history. They were there at the Big Bang in the form of pure energy. They were there when the first stars ignited. They've cycled through stellar cores and interstellar space, through countless transformations, eventually assembling into the specific pattern that is you. And tomorrow, when you wake, you'll still be part of this cosmic story. You'll breathe air processed by plants, eat food made from matter assembled by Earth's geology and biology, live under the light of a middle-aged star in an ordinary galaxy in a universe 13.8 billion years old. Every moment of your life unfolds against this vast backdrop of space and time. If you found this journey through cosmic time interesting, if you've enjoyed learning about the universe's age and the mysteries surrounding it, please take a moment to like this video and subscribe to the channel. Your support helps us create more content exploring the wonders of science and the cosmos. As you drift into sleep, carry with you the knowledge that you exist in a universe 13.8 billion years old, full of galaxies and stars, shaped by invisible matter and mysterious energy, expanding into an uncertain future. You're made of atoms forged in the hearts of ancient stars. You're a way for the cosmos to know itself, in Carl Sagan's beautiful phrase. And for this brief moment in cosmic time, you have the privilege of consciousness, of wondering, of learning, of understanding your place in the vast sweep of space and time. The universe is older than we can truly imagine. It's vaster than we can fully comprehend. And yet, we've learned to measure its age, to decode its history, to understand its evolution. We've peered back to the beginning and forward to the end. We've achieved something remarkable. knowledge of our cosmic origins and destiny. Sleep well, knowing that you're part of this grand story, this epic tale of emergence and evolution, of stars and galaxies, of matter and energy, of space and time. The universe is ancient, mysterious, and awe-inspiring. And now, for just a moment before sleep claims you, you understand it a little better. The knowledge you've gained tonight is not just abstract information. It's a connection to reality at its deepest level. When you look at the night sky tomorrow, you'll see not just points of light but distant suns, many of them older than Earth itself. You'll see galaxies whose light left them when the universe was young. You'll know that between those visible stars and galaxies flows the invisible cosmic microwave background, ancient light from the universe's infancy. You'll understand that the darkness itself is meaningful. The night sky is dark not because the universe is infinite and eternal, as people once thought, but because it has a finite age. We can only see light from objects whose light has had time to reach us in the 13.8 billion years since the Big Bang. This darkness, this cosmic horizon, is evidence itself of the universe's birthday. And you'll know that every observation, every measurement, every scientific discovery about the cosmos is part of humanity's ongoing dialogue with reality. We're asking questions of the universe through our telescopes and detectors, and the universe is answering through the light and radiation it sends us. Each answer leads to new questions. Each solution reveals new mysteries, and this process of discovery continues to unfold as we build better instruments and develop more sophisticated theories. The universe is 13.8 billion years old. Give or take 20 million years. This fact, determined through decades of careful observation and analysis, represents one of humanity's greatest achievements. We've read the age of everything in the structure of ancient light, in the motion of distant galaxies, in the chemistry of the oldest stars. We've looked back to the beginning of time and forward to the end, and found our place in the grand cosmic story. Good night, and may your dreams carry you through the cosmos, across billions of years of time, through clouds of stars and galaxies, back to the beginning of everything and forward to the end. The universe awaits you in sleep, as it awaits all of us in time. Rest now, part of an incomprehensibly vast and ancient cosmos, knowing that for this brief moment, you are here, aware, alive, and wondering. The age of the universe is older than imagination can truly grasp, and yet we've measured it, understood it, and made it part of human knowledge. Sleep peacefully in this understanding,